Okay, in our previous study, we see that both appears frequently in our argument. So it's convenient to give ball another terminology. Okay, so we have a remark. This ball center at A, which radius epsilon, is also called an epsilon neighborhood. Of A. So sometimes we use neighborhood. And now we have studied open sets and closed sets, and we have seen some examples of these two kinds of sets. The balls are opened, and the rectangle, which is the Cartesian product of two closed intervals, is a closed set. So a natural question is there other kind of sets? Can we find a set in Rn which is not open and not closed? The answer is yes. I will give you an example. Denote say 1, 2, 1, 2. So this say we said this say is neither open nor closed. Okay. Firstly, we draw a picture for this say to help us. Geometric picture is always helpful. So this is the coordinate system. So this is 1, 2, and this is 1, 2 in the y-axis. So this say is look like this. Because the first component of say 1, 2, this interval is opened on at the right end. Therefore, accordingly, the rectangle C, the right boundary of the rectangle C is not part of C. So we prove that this C is neither open nor closed. Firstly, we prove that C is not opened. Okay. To prove that C is not opened, we need to find a point in C which is not an interior of C. Okay. Which point in C is not an interior point of C? Obviously, for example, this point is not an interior point because any neighborhood of this point, that is any ball which arbitrarily small radius center at this point will contain some part not in C. This implies that this point is not an interior point of C, although this point is a point in C. Okay. So to see that C is not opened, we only need to see that for any epsilon positive, this point we give it a name B epsilon P is not contained in C. Here, this point P is this point. Okay. Why this is true? How to prove this? So we need to find a point in this this ball or the epsilon neighborhood or the P, but the point is not in C. Obviously, this point x, the coordinate of x is this point belongs to this ball, right? Because the distance from x to p, because the first coordinate of our x and p are the same, therefore the distance from x to p is the absolute value of the difference of their y coordinates. The y coordinate of p is 1, therefore this is, maybe I will give you more detail. 1 minus epsilon over 2, this is the y coordinate of x, minus the y coordinate of p, which is 1. The result is half of epsilon, which is less than epsilon. This implies that x belongs to the epsilon p, but obviously x is not in C. By the definition of C, any point in C has y coordinate not less than 1, but the y coordinate of our x is 1 minus some positive number, so the y coordinate of our point x is less than 1, so x is not in C. So for any epsilon, the epsilon neighborhood of P contains a point x which is not in C, so C is not an open set. Okay. Next, we prove that C is also not closed. A closed set is this kind of set. Any conversion sequence in this set has a limit still in this set. So to prove that C is not closed, we need to construct a sequence in C. The sequence is converged, but the limit is not in C. So which sequence in C has a limit outside C? Obviously, we can consider this kind of sequence. The limit is here. The limit lies in the right boundary of C. So we can write the sequence explicitly. Okay. So let a sequence PK is we can the x coordinate of PK should closer and closer to the 2. Therefore, we take it to be 2 minus, and this sequence is in C. Okay, and PK converge to a point. Because k goes to infinity, then this will converge to 2. This point is not in C, right? Because the x coordinate of the limit is 2. But any point in C has the first coordinate of any point in C is strictly less than 2. So our limit point is not in C. This implies that C is not closed. Okay. Well, our next topic is the relations between open sets and closed sets. So this is a theorem. Closed sets and open sets has very close relations. The statement is that S is closed if and only if the complement of S is open. What's the complement? We recall this concept. The complement of a set consists of the point in Euclidean space but not in this set S. In other words, the complement of S is the set obtained from removing S from Rn. So sometimes this is denoted by Sn, Rn removed S, or even Rn minus S. Different notation, but the meaning is the same. So this is the complement. Now we prove our theorem. Firstly, we assume that S is closed. We want to show that the complement of S is open. To prove that SC is open, we need to prove that every point in SC is an interior point. So for any point A in SC, we need to show A is interior point of SC, of the complement. Okay, this is what we want to show. If this is true, then the complement set SC is open, and we are done. Okay, so this is this part, the only if part. So for this part, we need to show that any A is an interior point of this. So we argued by contradiction. If this is not true, then for any epsilon positive, the epsilon neighborhood of A could not contain in the complement of S. Otherwise, A is an interior point of the complement, right? So this implies that this neighborhood has no empty intersection, which is no empty intersection. Therefore, this is true for every epsilon. We take epsilon to be 1 over k. Then the 1 over k neighborhood of A has no empty intersection, which is S. Therefore, we can take xk in this intersection. What we get? Then sk belongs to S, and the distance from xk to A is less than 1 over k. And this implies that xk converge to A. Xk converge to A. S is closed, and xk is a convergent sequence in S whose limit is A. Because S is closed, from these two facts we deduce that A is a point in S. This is a contradiction which our assumption at the very beginning. Our A is taken from the complement of S. Remember, at the very beginning of our proof here. So this is a contradiction. Therefore, this contradiction proves the only if part of our theorem. Okay. Prove the if part of our theorem. That is to say, the complement is open. This is our assumption. We will prove that the set S itself is closed. So to prove that S is closed, we need to show that the limit of any convergent sequence in S lies in S. So let xk be a sequence in S, and xk converge to some point, say A. We need to prove that A is in S. This is what we want to show. Okay. But we still argue by contradiction. If A is not in S, then A belongs to the complement of S. But the complement is open. This is open. So A is an interior point of the complement. So